Hello, my name is Nash Rockman, and in this presentation I would like to motivate how my current work supports AIM 1 in my statement of research. I'll discuss three topics: a coarse-grained model of vaccine escape, the molecular evolution of SARS-CoV-2 antibody evasion, and a global picture of endemic human RNA virus ecology, all leading to my proposed goal of evolutionary forecasting of endemic and epidemic pathogens. Consider a simple compartment model with one key population representing inoculated hosts. These are hosts that have been vaccinated and are building immunity, but are still significantly susceptible to infection, analogous to low-dose antibiotic exposure. Further consider two viral strains, the wild type and a vaccine escape variant. When the escape mutant is much less fit than the wild type, the sooner vaccination begins, y-axis, and the higher the rate of vaccination, x-axis, the smaller the cumulative number of infections, color. However, when the escape mutant is of similar fitness, there is a finite optimal rate of vaccination. We may now consider the impact of increasing or decreasing the rate of social contact for this small but critical inoculated compartment. Depending on the fitness of the escape variant, increasing or decreasing the contact rate of inoculated hosts may increase the cumulative number of infections by more than 25% or decrease infections by nearly 10%. So the conclusion of this first story is that we can predict over short timescales the effects of vaccination on viral life history traits. Now let's move on to consider the molecular features which can facilitate vaccine escape for SARS-CoV-2. We studied the structures of the receptor binding domain in complex with both the host receptor and antibody structures. Any mutation can be placed somewhere in this plane, determined by the degree to which binding to each partner is disrupted, and acknowledging that some mutations increase affinity. The position of any mutation in this plane depends on the background, and epistatic effects may be determined by assessing the change in position within this plane between the wild type and any variant. If the effects of all mutations are purely additive, there will be no change. Variant epistatic landscapes may be neutral, escape minimizing, or escape exacerbating. We demonstrated that overall, no escape exacerbating epistasis was observed, even for the Omicron variant background. Furthermore, looking at the distribution of mutations which increase the risk of escape, where the size of each letter is proportionate to the magnitude of this effect, we found that just a few key residues shared by both the Gamma and Omicron variant determine the nature of the epistatic landscape. This type of analysis may be employed at short evolutionary depths to assess the near-term landscape of RBD substitutions. Moving to longer-term trends, we built phylogenies for all non-segmented human pathogenic RNA viruses, with at least about 200 complete genomes available, in addition to H3N2HA. We then broke up each tree into lineages, identified as monophyletic groups or clades with a good fit for a date-constrained tree. These lineages break up the trees into groups of isolates which were apparently separated by periods of varying substitution rates, likely corresponding to different environmental conditions. We then measured the derivative of the number of parallel branches near the root and near the leaves for the real phylogenies and comparable trees built under a neutral evolutionary model. We examined the ratio of the simulated data over the real data, so this is the dark red arrow over the dark blue arrow evaluated at the leaves, and orange over light blue evaluated at the root. This gives us an idea of the rate of lineage turnover. All but one virus with two or more lineages identified displayed reduced lineage turnover relative to neutral expectation, indicating these lineages represent distinct ecological niches which do not compete over a shared population of susceptible hosts. These niches may be maintained by any independent opportunity for infection. This could be due to cross-immunity, regionality, or seasonality. Local niches are also possible when individual outbreaks are contained within smaller groups, for example schools or office buildings. We found that for more than half of all strains, there was no apparent seasonality, regionality, or significant cross-immunity suggestive of local niches. These data and analytical tools empower us to build actionable evolutionary forecasts for pathogens. While each event is stochastic, repeated trends are observed even in molecular evolution. We are already able to track predictable substitutions affecting receptor binding in real time. We can also predict how this mutational repertoire changes with a varying landscape of vaccination and prior exposure. Moving forward, we can leverage what we know about molecular evolution at an epidemic timescale to predict how measurable demographic and environmental shifts will change selective pressures and host adaptations on an endemic timescale. I acknowledge there are still significant challenges remaining with respect to data availability, but if we can expand and diversify our sequencing efforts to reveal missing sequences from intermediate hosts, we can begin to better understand the molecular mechanisms underpinning zoonosis and viral speciation, which I believe in turn will reveal fundamentally conserved features underlying the balance of adaptability and genome integrity extending into cellular organisms as I describe in part in my second aim. Thank you very much for your consideration.